So I just wanted to start with a quick live demo. You can try the program out for yourself by going to this web address, or you can scan this QR code. So this is the program running in Firefox. And we've generated a room here. If I press enter, it'll make a new one. And there we go, we've got a whole new layout with different materials, different colours. And yeah, we've got a few controls we can do, such as changing the quality, showing the room information. I'll just do one more. There we go. So I'll just jump back to the presentation now. So what is Procedural Content Generation, or PCG? I've written a definition here. It says dynamic creation of content through the use of random number generators, algorithms, and predefined objects. That's just a general term. It can be used for many things, including making the objects themselves. But it's used in a wide variety of fields, including video games, film, music, sound design, artificial intelligence, and simulations. So I've got a couple of pictures here. This is from Lord of the Rings: The Two Towers. And they use PCG to do the battles and crowds in CG. This is another picture here using Three.js, which is the same software graphics API used in this project as well. They simulated some plant vegetation. It says here, PCG in computing tends to be made using pseudo-random numbers. So that's quite important because we want a certain level of randomness, but not too much randomness, so that, you know, we don't want it to be chaotic. We want to control how random our simulation is. So how is it used in video games development? Well, it can be used for levels and worlds. You can see from these two pictures. This is from No Man's Sky, which is quite a popular video game where they simulated the entire galaxy using their PCG engine. And then this is a much simpler example. This is Spelunky 2, where you can see the squares are used to generate the worlds on a grid. So there we go, placement of objects and items, as you can see here, where they've put objects on the world. It can also be used for AI behavior, where we want to give the AI a bit more personality, a bit more randomness, so it's a bit less predictable to the player. So why use PCG for environments over handcrafted environments? Handcrafted environments basically means that the designer sat down and said, we're going to put this tree here, we're going to put this item here. While PCG is good because it has a lot of value in terms of replayability. So gamers really like their really good value products in terms of length of the game and how much content there is, and because it's so replayable, we're generating new rooms every time basically. Whereas, you know, handcrafted environment, you would play through once and you know where everything is, you know what's going on. It can use far less resources and memory, so unless of course we're saving the map, we don't necessarily need to hold all the data for the map itself. We can just generate it right there and then, scrap it, and then generate a completely new one. Adaptable and consistent. So yeah, if we say we're getting something spawning too much in the world, we can just say, right, we're going to tweak that, and that value is going to be less now or more depending on what we need. It's just the design is very consistent and very easy to alter. So here's some procedural generation techniques. There are a few used. We'll start with formal grammars. So formal grammars, aka grammatical systems, a set of rules defined by the programmer in which a string of characters is used to define content generation. So this here is Conway's Game of Life. This is a really famous example where it's a simulation that uses cells that are either on or off, and depending on how many are next to each other, this will define their behavior, and as you can see here, these ones are moving because of the rules they've been set. So that's the famous example. And then we've got L systems, which we start at a point, and as the rules go, we grow out, and it can make these random patterns basically. So you can see this being used for trees quite easily. And then there's Perlin noise, which is pretty well known, but if we generated a random one of these, we could use it to simulate how high or how low we want terrain to be. And then there's also constructive methods such as constructive solid geometry, which you can see here. These 3D geometries are created based on a preset and adding or taking away parts. That's how we can use PCG to create molded objects in different ways. So I just wanted to talk about the graphics API I used. Three.js was chosen. There are quite a few you can choose from online these days. The other most popular one is Babylon.js. They're quite similar. They both use JavaScript, but Three.js uses the WebGL as a framework, and of course WebGL is using computer graphics, OpenGL, the same creators. It runs in most internet browsers and is GPU dependent, so that is quite important. Although it does run in most internet browsers, it will be dependent on how good the person's computer is, how good their GPU is. Yeah, it's designed to be simple to use. It is very simple compared to WebGL. And it is a very powerful engine with loads of examples online. So I just wanted to talk quickly about the thoughts that went into designing these rooms. The first thing I did was I looked into some concept images I sourced online, and then I recreated these images in Blender just to see what was going on, what colors were being used, what sort of patterns can we pick up that can be used in the PCG engine. So one of the first things I noticed was that in most rooms we lay out the objects along the walls so that the people who live in them have space to get around. It sounds really kind of obvious when you think about it, but it's not something you think about all the time. But I thought that would actually translate really well to a grid when you think about it, because everything could be given a set size and then we can generate it that way. And the other thing I noticed was interior designers like to use color a lot, and yeah, you can see from these pictures we've got these really nice colors with colors that work really well together. So I thought, oh, maybe we could do something with that in the engine as well. So this is how the grid is generated. We give Three.js a grid helper, and we give it a set size of 1000. It can be whatever we want, but for this one I went for 1000, and then with 20 divisions. And then to get the grid cell size, we can just do grid size divided by grid divisions, which is 50 pixels both ways. And then it's really easy just to spawn an object on the grid. We just put its position as the X and Z coordinates. So this would be 0, 1, 2, 3, 4, 5, and then 3, so 0, 1, 2, 3. But a problem emerges here because if we want to rotate the object, we wouldn't want a chair facing a wall, we want it facing away from a wall. So I needed to figure out a way to get that working, and that's where Euler logic comes into play, where because this particular object has a grid offset to make sure that it sits directly in the middle, If we just rotate it without using the Euler, it'll rotate it its local position, and that's why it's going off a bit here. So we come down here, you can see we start with the offset in a vector 3, and then we create a Euler that's got the rotations we want, and then we apply the Euler to the grid offset, and then if we add that to the position we want it on the grid, and spawn it, there we go, it's rotated the correct way. This is how objects are populated in the room. I use ASCII map, I call it, so that's just printed to the console here, but it's just a 2D array that contains the positional data of the map, and it's flush with the 3D view. As you can see here, the grid is generated, and then we've got this is the walls with an X, and then we've got TT, which is a table, and there's a study area here, etc. And to do that, we just use a for loop to initialize the 2D array once it's created with the X's, and then basically when the objects spawn into the room, we know that nothing else can spawn here because it'll have to check. It'll have its own set area. Object groups, as you might have seen, some objects are grouped together so that they make set areas. For example, this here is a study area, so we can see that although it has the same amount of objects, it's using different objects randomly per generation. And then this is how the object groups are created. We just go through the for loop along each wall, so along, then down, and then back again, then up again to the start, and each time we're checking the cells in the 2D array, and if there is a space we can spawn. If there's not, then we just keep moving on, and then obviously there's a random number as well that says, oh, you know, there's a chance that we just won't spawn this at all anyway, even if it is a space here. And then once the group objects are done, we can also add in singular objects afterwards once the whole thing's done. So it's not just group objects, there's also singular ones as well. So wall objects work a bit differently because there's no set area on the grid for wall objects, obviously, but instead we have to use access aligned bounding boxes, or AABB. In Three.js that would be a box 3, and it just creates an area around the object for checking collisions, basically. And then this is how the collision is checked. Once all the objects spawn into the room, the wall bounding box is checked against all other bounded boxes. This is the parent and child objects part, where I really like this part. Basically the idea was that to make each object a bit unique, it has a set of child objects it can use and spawn on top of its areas. Here you can see different examples of that, and this is how we do that. So yeah, if you look at this part here, this is a setup that needs to be done for every object in the scene, where we're saying all the information we need before spawning, and then you can see here the object slots for each of these areas, and we can see the type of objects that could spawn on this particular object. And then we've got color harmonies and materials. So this is an OBJ file, and then there's an MTL file that comes with this OBJ file, and you can see it's got the sofa and the legs, and we can apply separate materials based on this. So this is the model setup again, and you can see some of the acceptable materials this armchair can take. So it could only take leather and wool, and the PCG engine will choose these randomly. And it also is set to flush, which means that if it picks leather, then it will be leather for the front, the base and the front. But if it was set to false, it could be leather and wool if we wanted to, but it might look a bit strange. Some objects use it, some objects don't. And then this is how we apply the material. When the object is loaded, the MTL file is loaded as well, and then we just replace the material with the one we've assigned in the PCG engine. Just quickly talk about color theory. So what I did for this project was I looked at the room examples I mentioned before, and I just looked and counted the amount of colors that are being used in each room and put them into percentages, and then the engine just picks one of these random schemes, and then all of the objects can choose any of these colors based on their percentage chance. And I got the idea from No Man's Sky again. As you can see here, we've got a planet that could be generated, and the creatures that spawn in these areas. So here's the results. I haven't got much time, so I'll just quickly show this. As you can see, it is the same room here, but it kind of makes the room look a bit different each time because we're using different color schemes. And then this is a typical material, so this is wood cherry, and then it sort of shows you the presets need to be made, like the roughness, the metalness, clear coat, and the texture maps it uses. And then there's a bird ornament here that uses this material in its list of PCG materials that it could possibly use in a scene. And then it's applied when the PCG engine happens. We just go through all of those and say pick one, and we'll change it when it loads, as we saw before. And this is the results. You can see this bird object looks quite different when it's got the wood cherry applied, and then we're moving on to a sort of plasticky sort of color. And then this is a leather couch. And now it'll be a wool couch. So yeah, it's cool. It can give you all sorts of different presets. So thank you for watching. That was my project. I really enjoyed working on it. I'm really proud of the results. There were a few problems, but overall I'm really pleased with it. So thank you very much for watching.